Christopher. This is my screencast for problem 14 in the text. My goal is to reassess the standards 1.5 that I can use the momentum principle to solve problems, and standard 1.6 that I can draw and interpret velocity, momentum, and force versus time graphs. So the problem starts off, and it wants me to say which of the possible diagrams corresponds with the correct overhead view of the block. I chose B because FNet is applied immediately, so it's not C, which curves like that, and it's unchanging, so it doesn't curve like A, which goes like this. Next question asked me which components of the block's momentum were changed by the impulse. Because the impulse is perpendicular to the original motion, because the original motion is like this and the impulse is like this, only the z component is changed. Next up, I was asked what is the unit vector, and I found that from the angle. So looking at the angle with which the ice is at after the impact, I found cosine of it for the x and sine of 22 for the z. Next up, I knew to do this because the unit vector is independent of magnitude. The unit vector is simply the relationship between the components, which can be found from a simple angle. Next up, I was asked the x component of the block's momentum after the kick, and momentum is simply theta times mass times velocity. In a non-relativistic, this guy is roughly equal to 1. So to find the momentum in the x component, I multiply the x component's velocity times mass to equal 1.75 meters per second per kilogram. Next up, my goal is to find the magnitude, and the momentum vector is equal to the magnitude times the unit vector, and the magnitude is a relationship between magnitude is a relationship between a component and its unit vector. So I was able to find this relationship by just using the x component and the x component's unit vector, 2.5 meters per second over 0.927, and I defined the magnitude was equal to 1.888 meters per second times kilograms. So I say there should be the same relationship with each component. Moving on, I decided to model this. FNet is constant. We're assuming that FNet is constant over this interval, or that at least FNet averages, and the time interval stops at 0.033. After the foot leaves contact with the ice, it doesn't affect it anymore. The momentum in the x direction stayed the same, no change. Momentum in the y direction, we're not worrying about that. Momentum in the z direction changes positively until it reaches the point where the foot leaves impact with the ball, with the foot leaves impact with the ice, and then it doesn't decrease, it simply stays at the level it was. Moving on, I was able to find the z component of the block's momentum simply because if we look at this, using the momentum principle, which is vector pf is equal to vector pi plus fnet, that should be a vector sign right over here, times change in t, so graphically with vectors, pf is equal to pi plus fnet. But I was able to find the z component simply by using the magnitude I found from the previous problem and multiplying it by the unit vector for z, which we found over here. Anyway, this gave me that the z component of the block's momentum was 0.707. So putting everything all together, pf was equal to 1.75, 0, 0.707 meters per second times kilogram. And then finally, I was able to find the magnitude of the average force applied, because using the momentum principle, change in p is equal to fnet, vector fnet times change in t. Thus, isolating fnet is equal to the final momentum vector minus the initial momentum vector, all divided by change in t, which I was able to do leaving me with an answer of F average is equal to 235.7 newtons. Thanks for listening. I hope you have a good evening.